Aloha, my name is Nicholas Ulm. I'm a PhD student in the Ocean and Resource Engineering Department. I'm the recipient of this year's L&M Koenig ARCS Award in Ocean Engineering. My research looks at how to integrate a self-driving ocean wave energy buoy with a mobile autonomous underwater vehicle docking station. My dissertation focuses on how the shape of the buoy can be optimized to improve power production, while creating a stable enough platform for an autonomous vehicle to dock to. The geometry of the buoy is based on the shape of the Halona blowhole on Oahu, which gives the device its name. As a wave enters the hollow chamber filled with air, it compresses the air and forces it through a fan to extract electricity. The present design is inspired by an ocean drifter. This will allow it to use ocean currents to propel itself over basin-wide distances. By utilizing known oceanic current patterns, such as mesoscale eddies or the Gulf of Mexico loop current, power does not need to be expended to drive the buoy from one place to another, but instead simply navigating it in the background flow and letting the current drift it to the desired location. We developed this device to enable ocean scientists to observe ocean phenomena at a reduced cost with a smaller carbon footprint, while also improving our ability to observe the ocean. Presently, the ocean is vastly undersampled due to limitations of resources and the risk to marine operators. Current methods of ocean observing often involve measuring an essential ocean variable, like temperature, at one place in space and time. These methods require techniques that often trade resolution in space or time to accommodate power limitations. Ocean observing methods that aren't power limited are often fixed infrastructure, which require frequent maintenance by marine operators. In many parts of the world, access to the infrastructure can be limited by prevailing conditions, which can inhibit access to infrastructure for months. Additionally, these observations are limited to a single point in space, which limits deployments to a suitable location that may not coincide with areas of interest. By enabling autonomous vehicles to charge at sea, without the use of oil, and without the need for a ship to be continuously present, we can observe the ocean in greater detail for longer durations with larger global coverage. With anything we deploy in the ocean, we want to make sure that the instrument will function properly and will not pollute the ocean. For this reason, developing wave energy buoys is a slow, iterative process. The first step is always jumping into a pool, making waves, and observing how the buoy behaves. From there, you build it bigger and test it in what's known as a wave tank, which is a really long pool that can make waves. We verified that it performed as expected, and then scaled it up to a 1/10 scale prototype. This past spring, we tested the 1/10 scale prototype, which is about 50 pounds, in what's known as a wave basin. The wave basin enabled us to send waves that are more similar to ocean conditions, with waves being generated at different angles. We tested the buoy in the same conditions that we find in the south shore of Oahu to make sure that it worked properly and that a place that we intend to test it next. This past spring, additionally, we also submitted Halona into a joint design competition sponsored by the US Department of Energy and NOAA, where we developed a version of the buoy with the intention of improving hurricane monitoring. Our design was selected as a winner of the stage, and now we are tasked with building a fully functional version of Halona that will be tested in January at the US Navy Mask Basin. If you're interested in joining the project or learning more, check us out at uh.halona on Instagram or email me at ulmn@hawaii.edu.